Hello everyone, welcome to the 17th lecture. So, we will continue with the development of point groups that we started in the last class. So, last class we sort of ended at a stage where we said we developed the point groups up to the orthorhombic crystal system, and then so we looked at its holohedral point group, which is MMM or 2 by M, 2 by M, 2 by M, and counted the number of symmetry operations in this point group, and there were 8, and this point group also consists of one bar, and which is the inversion operation, and any point group that contains the inversion operation, we define that to be a centrosymmetric point group. And we will see why centrosymmetry is important in understanding various materials properties. This is one of the major symmetry elements that even if you do not know symmetry, everyone sort of speaks about this, and it is very crucial to understand what centrosymmetry is. But centrosymmetry is very simple. If the point group consists of one bar operation, then that point group is called a centrosymmetric point group. Simple. Okay. So, we will continue there, with that, and we have listed out all the groups so far, or examples of groups that are centrosymmetric, that are non-centrosymmetric, right. So, we will continue from where we have left off. So let us go back to the orthorhombic crystal system. We said one of the point groups is a 2 2 2 point group, right, and a 2 2 2 point group, if I am going to represent it in the symmetry diagram, what I have is so let me just draw these two axes, right. So, what I have is so this axis, or the x axis has a two-fold axis of symmetry. So, that is going to be how I represent a two-fold axis of symmetry. The y axis also has a two-fold axis of symmetry, which is I am going to represent it as like this, and the c axis also has a two-fold axis of symmetry, which I am going to represent it like this, right. So, this is the stereogram of 2 2 2. Okay. Now, I said that I am going to separate out the representation of asymmetric elements from the stereogram representing just the symmetry elements, symmetric units from the stereogram just representing the symmetry operations. So, if I do that, so I start with an asymmetric unit here. This asymmetric unit should undergo a two-fold. Let's apply the first two-fold axis of symmetry, which is along the c axis. So, this thing will come here, right. And now I apply another two-fold axis of symmetry, which is about this axis, right. So, then it goes behind, right. The chirality remains the same, right. So, we are in this picture, we are not getting we do not understand the chirality yet, but that is okay. We will put in as and when it is necessary, right. And then so there is again two-fold axis of symmetry about the c axis, and this point gets reflected here, right. So, this is how the asymmetric unit looks like. Okay. So, this is how you develop the symmetry operations, right. So, now if you see if you see this stereogram, you understand that there is no inversion symmetry here. This point is not going inside the plane. The xyz is not going to minus x minus y minus z. Rather, there is the only thing that there is here is a two-fold axis of symmetry. Okay. So, there is no inversion, no one bar operation, right. Okay. Now, we can do the same thing for MMM, which is it has more symmetry elements in it, right. So, the way I am going to represent the symmetry operations, the stereogram with just the symmetry operations is as follows. So, I am just going to say that the plane itself is a plane about which there is mirror symmetry. This is a plane about which there is a mirror. Then I am also going to shade the x and y axis. Perhaps I can just use a thinner one, right. So, just give me 1 second. That is okay. I do not think I can thin it down even more. So, this thicker line means that I have a mirror about this axis, and I have another mirror about this axis. So, these are so they should be equally thick ideally, right. So, okay, so you can try to shade it so that they are equally thick or equally unthick, right. Okay. So, I have 3 different mirrors, right. So, Now, if I have 3 different mirrors, I said that is sufficient in general, the other operations just reflect. Okay. But so what are these other operations that reflect? So, I have a two-fold axis of symmetry. So, maybe I can just use a different color to show that this is a two-fold axis of symmetry. This is also a two-fold axis of symmetry, right. So, there in this plane I have two different two-fold axes of symmetry, the 1 0 0 and the minus 1 0 0. Now, why is this? So as of now it is very intuitive, but when we do stereograms this becomes more obvious as to why this is 1 0 0 and this is minus 1 0 0. Okay. This is the 0 1 0 and this is the 0 minus 1 0, right. So this is the symmetry diagram in general, right. So this is the symmetry stereogram of MMM, right. Now, if I however plot so this is a mirror, I am going to just shade it, right. If I have, and this is another mirror. So, ideally I can just mirror it, I can just use 3 mirrors and then get to all the asymmetric units, because the other two-fold axis of symmetry just come from mirroring it thrice, right. So the mathematics will take care of it. So, if I have an asymmetric unit here, then because of this mirror I am going to put the same asymmetric unit here, okay. And then this mirror would translate would put this asymmetric unit here, and then this mirror would put the asymmetric unit here. But also so there is another mirror which is this mirror, the mirror about the c axis, perpendicular to the c axis, that will put the asymmetric unit inside. So, I am just going to put a dot inside the circle, right. So, the chirality is different, but that is okay, right. So, and then that will put another dot inside the circle, right. So, I have all these different elements coming from 3 mirrors, right. So, in fact, you can see here that if I have a circle, an open circle here, I have a dot here, and these are related by inversion, right. So, I have a 1 bar operation, right. So, just by looking at the stereogram I can say that there is a 1 bar operation that exists here, okay. So, this is how one represents the stereograms of these low symmetric crystal systems, low compared to cube, right. So, we are going to cube very soon, okay. So, next we go to the tetragonal system, right. Now, we said anything can be defined as a tetragonal system if it has at least one, if it has one four-fold axis of symmetry, right, not at least, only one four-fold axis of symmetry. So, I have a four-fold axis of symmetry and nothing else, okay. So, that itself is a point group, right. So, then this will have 1 and 4, right. I have a 4 bar axis of symmetry, that is also tetragonal, right. So, 1 4 bar, right. And 4 bar, so I said this is 4 bar, and 4 bar does not necessarily need to have symmetry, right. So, sorry, inversion symmetry. 4 bar point group does not have inversion symmetry, 1 bar in it, right. So, this is not centrosymmetric. That 4 is not centrosymmetric is obvious, right. But that 4 bar is not centrosymmetric, just because there is a bar on the top of 4 does not mean it includes 1 bar in it, right. So, this is also not centrosymmetric, and we looked at this, right. So, we looked at the operation 4 bar, we looked at its stereogram, and we said why this is not centrosymmetric, okay. By the way, so a 4-fold operation should also have a 2-fold operation in it, right. Similarly, a 4 bar will also have a 2-fold operation in it, right. You can actually look at a 4-fold axis of so if this is my 4-fold axis, then I have an asymmetric unit here, 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 here. So, by default I will have a 2-fold axis of symmetry, okay. In fact, yeah, so the 1 0 0 axis, the c axis is also a 2-fold axis of symmetry, whereas 4 bar will have so 2 units here and 2 units here, and this also has a 2-fold axis of symmetry, right. So, the 2-fold comes for free. If I have a 4-fold axis of symmetry, the 2-fold comes for free, okay. Now, can I do something else still retaining this to be tetragonal, right. So, for tetragonal the highest symmetry I should have is the 4-fold axis of symmetry. Let me add another 2-fold axis of symmetry. So, this is the first point group, this is the second point group, right. So, I am not going to derive every point group, but I am going to just tell you the way of developing all the point groups, right. So, if I add another operation, right. So, I have a fourfold axis of symmetry, then I will have a perpendicular axis which also, and this fourfold axis of symmetry anyway has a twofold axis of symmetry, right. So, I will have a perpendicular axis which has a twofold axis of symmetry, right. Alright. So, there is fourfold about let us say 1 0 0, there is twofold about let us say 0 1 0, right. Then what comes for free? Of course, so if there is or okay, so let me make this 0 0 1, then it becomes easy. This is 0 1 0, right. Oh, sorry, just excuse me. So, this is about 1 0 0, this is about 0 1 0, okay. So, alright. So, this is fine, because if there is a fourfold axis of symmetry, there is also a twofold axis of symmetry about 1 0 0, there is also a twofold axis of symmetry about 0 1 0. So, of course, there should be another twofold axis of symmetry about 0 0 1, right. So, our 2 2 2 is sort of all the elements of 2 2 2 should be in 4 2, right. At least all the elements that are present here should be in 4 2, right. So, this is what will be called a subgroup of 4 2 2, okay. Or subset, right. So, you would have studied sets. So, all the elements of this set or this group are elements of this group, right, and this group has even more, right. So, this group will be a subgroup of 4 2, right. But there is something else that comes up. It is not a twofold axis about 0 0 1 comes up, that is there, but so fourfold axis of symmetry about 1 0 0 and a twofold axis of symmetry about 0 1 0 gives you a twofold axis of symmetry about 1 1 0. So, this is a diagonal twofold axis. Okay. This is not the perpendicular, it is not the orthogonal twofold axis to 0 1 0, rather it is the diagonal twofold axis. The orthogonal also exists, right, but that is just by virtue of me having a fourfold axis of symmetry. Whatever happens about 0 1 0, the same thing should happen about 0 0 1. So, I am not going to just represent that, right, that anyway exists, that is obvious, but what exists and that is not obvious is if I multiply these two operations, what I get is a twofold axis of symmetry about 1 1 0, okay. Now, I want you to go home after this class, I can derive it, but I want you to do it. So, take the matrix for fourfold axis of symmetry about 1 0 0 as P, take the matrix of twofold axis of symmetry about 0 1 0 as Q, look at what PQ is and prove to me that PQ is nothing but a twofold axis of symmetry, prove that, right, is a twofold axis of symmetry about 1 1 0. Now, if you are getting confused about the matrices, you can use the appendix of Burns and Glaser, one of the textbooks recommended for this course, has all the matrices, all the symmetry operations, okay, relevant matrices for all the symmetry operations. Okay. So, the point group, okay, so just go back and do this as an exercise. You can refer to the matrices in Burns and Glaser, prove to yourself that if there is a fourfold axis of symmetry along the A axis, if there is a twofold about the B axis, then I get a diagonal which is twofold axis of symmetry. Okay. All right. So, in that case I will show you the stereograms later, but yeah. So, the point group that I have then, that I have developed so far is actually 4 2 2, but this 4 is 1 0 0, this 2 is 0 1 0. So, this 2 will be 0 1 1 0. Okay. So, yeah. So, that is the point group that we have developed. Okay. So, similarly I can have 4 bar, right, and I can have a twofold axis of symmetry. What I develop is a diagonal mirror. Okay. So, that is the other point group. We will look at the stereograms of this. So, this is point group number C, this is or 3, this is point group number 4 and so on and so forth. Okay. So, so I can have multiple operations, right. So, I am actually combining a 4 bar along with 2 bar and M, and I am not losing the tetragonal system, right. So, the system is still tetragonal, right. So, because the highest symmetry I have is a 4 bar axis of symmetry, right. Okay. Yeah. So, let us look at so the other one I can do is just 4 cut with M and that is it, a 4 by M, right. So, 1 1 rather, right. So, I have a 4 fold axis of symmetry which is cut with M, and then this one will be centrosymmetric, right. The other point group I can have is, instead of having 4 2 2, I can have 4 M M, right. And so if I have 4 and M, the other diagonal mirror comes for free, and so that is so that is actually not going to be centrosymmetric, right. And then so the other point group I can have by combining various operations is, I will have a 4 by M and then M M, right. So, so this is again a centrosymmetric point group, and this becomes the holohedral point group of the tetragonal system. Okay. All right. So, so these are the various point groups, and any other combinations will either belong to these point groups or will not satisfy the condition that what I have is a tetragonal system, right. So, so these are the 7 combinations you can have as point groups of a tetragonal system. Now, if I want to actually look at the stereogram of let us say 4 2 2. Sorry. So, let me just make a small correction here. So, this 4 fold axis is about the C axis, and then if I have 0 1 0, I will also have a mirror in the plane, right. So, mirror is actually the perpendicular to the mirror will be the 4 fold axis. So, so let me correct that. Okay. So, so this should be 0 0 1 and this should be 1 1 0. Okay. Okay. So, let us draw the stereographic projection of 4 2 2, right. So, let us just have the symmetry elements first. I have a 4 fold axis of symmetry here, right, and then so these are, nothing is a mirror, right. So, these are all thin lines are not mirrors, they are just axes, right. So, as a result of having, I mean, so 4 and then so perpendicular to 4 fold is a 2 fold axis of symmetry, right. So, this is one 2 fold axis of symmetry, since this is a 2 fold axis of symmetry and this is a 4 fold axis, right. I should automatically get the other so just by virtue of there being a 4 fold axis of symmetry about the C axis, I should get the other 2 fold axis of symmetry, right. So, the 2 fold axis of symmetry also is symmetrically rotates, you rotate this by 90 degrees, the symmetry should retain, right. So, because this is a 4 fold axis of symmetry, but what else do I have? What I have are actually the diagonal mirrors, right. So, I have the mirror plane about 1 1 0, right. So, that is the diagonal mirror, and I have another mirror plane about 2 fold axis, not mirror. I have 2 fold axis about 1 1 0, and I have another 2 fold axis about 1 minus 1 0 or something like that, perpendicular to that, right. So, the perpendicularity is always maintained, right, in plane. Okay. So, all these are the various symmetry operations you will have when you do 4 2 2, right, for example. And then you can also look at the asymmetric unit, how the asymmetric unit changes, right. So, I can start with an asymmetric unit here. Now, so eventually what I will end up, and you can do this exercise yourself, right. So, if I have plus, so I'm again, so I can as well represent this with dot, but I am just going to do plus and minus. So, if I have a plus here, I have minus here. If I have plus here, I have minus here, and if I have plus here, I have minus here. Right. So, and So that gives you the two-fold and four-fold axis of rotation. So 4 2 2 is the asymmetric units actually line up like this. Okay. So this is how the stereogram looks like. Now I am going to show you some because I can draw all the stereograms, but then that becomes very time consuming, but I am just going to show this to you on a PowerPoint, right. So just going back, these are all the tetragonal point groups. We started with tetragonal point groups. Here is the full symbol, here is a short symbol, right. So if I have something like okay, so let me just go and clarify one thing. So 4 by mm means that this is also equal to, just like I said, if I have 2 m's and this is also a two-fold axis of symmetry. So this is equivalent to 4 by m, 2 by m, 2 by m, right. But instead of writing 4 by m, 2 by m, 2 by m, I am just going to write it as 4 by m, 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 right. So this is the longer symbol and this is a shorter symbol, right. So that is exactly what I am going to show now in the slides. So for example, yeah, so this is a longer notation of the holohedral point group and this is a shorter notation of the holohedral point group, right. Just by having four-fold axis of symmetry and then adding other operations, I can have 1, 2, 3, 4, 5 different operations, and by having 4 bar I can have 4 bar and 4 bar 2m, right. Now I can have 4 bar by m and all these things, but that will turn out to be 4 by m, right. So there is no specific advantage by having 4 bar by m. This will be one of the other point groups, right. So I would have double counted it. I can have other operations like 4 bar by m, 2 by m, 2 by m and so on and so forth, but that will be one of these operations. Okay. So you have 7 different point groups coming from a tetragonal system. Okay. Now so here is a list of all the different asymmetric units and the stereograms that I have been talking about in all these systems. So in a monoclinic system, so the this is C axis is the two-fold axis, right. So here I change that so this is the C axis is perpendicular to the mirror, right. So that is the monoclinic system, here is the triclinic system and so on and so forth. You can refer to this to this graph to this chart to actually see what are the various symmetry elements. So the stereogram for symmetry is here, the stereogram for asymmetric units is here. So you can refer to this chart and always understand whether a certain symmetry element is there or not there. For example, I tell you MMM or so for example 2 by m, right, does it have inversion symmetry? Of course it has inversion symmetry. I can just look at this and tell you that there is inversion symmetry, right. So these 2 points are inverts xyz and minus xyz of each other. The chirality also changes, right. So the chirality is not represented here, but the chirality also changes, right. I can ask questions like what is there a so by 4 2 2, right. So what I mean is well, so how many diagonal mirrors are there? What are the various what are the various two-fold axes, right. So the two-fold axes are not just 0 1 0 and 1 0 0, but the two-fold axes are also your 1 1 1 0 and 1 1 bar 0, right. So just looking at the stereograms you understand all the various symmetry operations that also are generated by a combination of various operations, right. So this is a very nice visual representation of of all the operations multiplied together and then giving you a two-dimensional projection of a three-dimensional symmetry. Okay. Okay. So with that I have to go to cubic system now, right. But before doing cubic systems, I have been saying that whatever I am showing you here are all what are called stereograms, right. Even in cubic system, the number of symmetry operations are just going to get larger and larger. I already have 4. You see here, so I made some piece with it. I have maximum 1 axis, right, which has highest symmetry, and this axis up to the tetragonal system, right. So this axis is called the principal axis. I have the maximum symmetry about a principal axis, and I have other symmetry elements about what are called the dyad axes, which are not the principal axis. Okay. And I have made some form of, even without understanding what stereographic projection is, I said okay, so I have all these 3 axes which are orthogonal to each other, and the third axis is coming out of plane, and I use some notation to say that okay, if this has 4-fold, this has 2-fold, this has 2-fold, so I am just going to put circles and these ellipses, elongated ellipses and so on to represent the symmetry operations, and that worked so far, right. Now, what I am fundamentally doing is actually I am looking at what is called a stereographic projection. But in such simple cases where I have only one principal axis, it didn't really matter. I didn't really have to understand what stereographic projection is, right. But when I go to more complex cases of a cube, for example, a cube by definition should have at least 4 3-fold axes of symmetry, and all these 4 axes are not orthogonal to each other, right. Now, how am I going to represent it in the form of a circle and then show you that so a circle which is in the plane and show you that there are these 4 different 3-fold axes of symmetry, right. So, then we actually now we have the motivation, or so we have the reason to actually learn what a stereographic projection is and how elegantly can it represent all the different symmetry elements in the form of a circle, right. So, in the form of an equatorial circle, right, of a 3-dimensional object. Okay. So, let us actually take a small detour before going to cubic systems and look at what are called stereographic projections. Very small detour. I am not going to spend a lot of time in explaining what stereographic projections are. Okay. So, I have earth, let us say, right, this is the equator of the earth, or I have a sphere rather. Let us say that is the north pole, that is the south pole. Now, I have some point P on the north pole, on the northern hemisphere, right. So, P is a point in the northern hemisphere. Right. It is a 3-dimensional object, a sphere, right. However, so all I am talking about is points that are on the surface of this sphere, right. So, the effective dimensionality of this surface of the sphere is 2, right. So, instead of looking at it in some sort of a curved manifold, right, so which is the sphere, I could rather project it onto my equatorial plane in some way and then say that so and then look at it as just a planar representation, right. So, that is what is called a stereographic projection. So, the easy way of doing it is any point on the northern hemisphere, we will just look at one half of the hemisphere, right. So, we do not want to complicate things by looking at points on the other half. So, any point on the northern hemisphere, I am just going to draw a line, connect it to the south pole, and then say that the stereographic projection of that P dash is here, right. Now, so the point the north pole itself will be the center of the stereogram, right. So, this is the north pole, and these points do not really change, the edges of the equator, the equatorial points really remain on the equator, right. So, edges of the equator, right. So, all the other points fall on this circle, the equatorial circle, but inside so inside the circumference of the equator. Okay. So, that is a simple way of understanding stereographic projections. Now, so let us the length of the stereographic projection will be related to the phi angle alpha with which this so the azimuth of the point P on which it is on the sphere, right. So yeah, that is essentially stereographic projection. Okay. So, now we use this stereographic projection in case of a crystal, right. So how are we going to use this for the case of a crystal? So, we are going to say in a cubic crystal, right. So, in a cubic crystal this becomes easier to understand, but you can do exactly the same thing to any other crystal. So far we have shown that up to tetragonal crystal we do not even need to understand the idea of stereographic projection. Okay. In cubic it becomes more difficult. So we try to understand we have to go into the construct of a stereogram, right. So in cubic crystals, so let us assume that there is a crystal, right. So and this crystal has various directions, right. So this direction is the 0 0 1, right. So my north pole has a direction which is 0 0 1, right. So this is this crystal, this cube is at the center of the sphere, right. So the directions of the cube are defined by so the north pole is 0 0 1 direction. For example, the 0 1 0 direction, which is just the is somewhere here, right, 0 1 0. Then I have and so on and so, sorry, not 0 1 0, 0 1 0 is here and 1 0 0 is behind, right. So it is on the equatorial plane itself, the 0 1 zeros and 1 0 0, right. Whereas so 1 1 1 is somewhere here on the sphere, 1 1 1 is the body diagonal, right. So I am just going to then project this 1 1 1 with respect to the southern hemisphere and then say that the 1 1 1 is going to be on the equatorial plane, right. So that is how I am going to represent the 1 1 1 direction, right. So similarly I am going to represent the 1 1 1 minus 1 direction as another point on this equatorial sphere, right. So I instead of looking at all these directions spread over a sphere, a hemisphere, I am going to look at all these directions on a stereogram. Okay. So if I do this projection exercise in a cube, right. So for example, here I think the notations are slightly weird. So here the idea is this is the north pole and this is the south pole. So the cube is the sphere is sort of rotated such that out of plane is north pole and into the plane is south pole, but that is okay, right. So I can always rotate it back and make north pole point up and south pole point down, that is fine. Now with respect to that, right, so I can take projections and so my north pole is 0 0 1, so north pole becomes the center, okay. So forget all these triangles and other things, but so just look at the spots, right. So where are the spots? So this is the 0 0 1 direction, right. So I am going to represent this as my north pole or 0 0 1 axis or 0 0 1 direction. Now so this will be these are the 1 0 zeros and 1 bar 0 0. Similarly 0 1 bar 0 and 0 1 0 are on the equators, right. So they are actually perpendicular to the c axis. The c axis is the 0 1 0 0 0 1, okay. And so you see that the 1 1 1s, the 4 body diagonals come up here, right. So this is 1, this is 2, this is 3, this is 4, the 4 body diagonals, so I can just make roughly, if I have to just give you a hand waving pictorial hand waving representation of the stereogram, I have so I am going to draw something like this. This is my center of the stereogram, this is 0 0 1, right, and this is 1 0 0 and this is 0 1 0 or the other way around, right. So and then I am just going to draw these sort of circles and then I am going to say that the intersections here are my 1 1 1s, right. So this is 1 1 1, this is 1 1 bar 1 and so on and so forth, right. So the 4 body diagonals. Now we also have the 0 1 zeros, the 0 1 1s, right. So the center of these sort of equatorial line, these sort of longitudes, right. So these become some sort of projections of all the longitudes. The centers of these longitudes become 0 1 bar 1, 0 1 1 and so on and so forth, right. There are so there is a 1 1 0, 1 1 bar 0 or so 1 bar 1 0 which is actually perpendicular to 0 0 1. All the directions, all the diagonal directions, all the 1 1 zeros which are perpendicular to 0 0 1 are on the circumference, right. Whereas the ones which are not perpendicular, for example 0 1 1 is not perpendicular to 0 0 1, they fall here, right. So just looking at the stereogram, I can make a mental note of what are the different directions. The important directions in cube are 0 0 1s or the family of So I am just going to write it as follows. I use an eraser, I erase this. The family of 0 0 1 directions, the family of 1 1 0 directions, and the family of 1 1 1 directions, right. So, if I can understand where these points are, then I sort of, and these directions and these points tend to be points of highest symmetry, right. So, if I can understand where these points are in a stereogram, just look at it and understand it, then I am fine, right. So, I look at the stereogram and I know that this is 0 0 1. On the circumference are 1 0 0 and 0 1 0, but on the circumference are also the 1 1 zeros which are perpendicular to the 0 0 1, but those are at 45 degrees to the 0 1 0, right. So, that is, these are all the this is simple geometry, okay. Whereas the other 0 1 bar 1, 1 bar 0 1 and so on and so forth, which are not perpendicular to 0 0 1, fall, so they are at an angle. This defines the angle between 0 0 1 and 1 bar 0 1, that is not 90 degrees. So, that falls at 45 degrees in fact, right. So, that falls in between 1 bar 0 0 and 0 0 1, right. And then you have these 1 1 1s which are just displaced, so they are, I can draw two different longitudes, the projection of two different longitudes, and wherever these longitudes intersect, that is where the 1 1 1 the body diagonals are projected, okay. So, this is just internalize this picture, internalize this, so that next time even if I do not say that this is 1 1 1, you say that the intersection between all these longitudes actually gives me 1 1 1 direction, right. So, in the stereogram, okay. So, all right, with that as the background for stereographic projection, let us look at cubic systems, okay. Now, cubic systems, what do we have for cubic systems? We have 4 3-fold axis of symmetry. And typically if I draw a cube, all these 3-fold axis of symmetry are nothing but the body diagonals, which are the body diagonals, right. So, now these body diagonals are just 1 1 1 1 1 bar 1 1 1 bar, right, then 1 bar 1 1 and 1 1 bar 1, right. So, these are the different body diagonals I have and the negatives of them, but it is the same line, right. So, we are just going to use 4 different body diagonals, okay, using this notation. So, these are all 3-fold axis of symmetry, okay. So, if I have 4 3-fold axis of symmetry, right. So, do I get an additional symmetry about one of these, so about 1 1 1, will I have any other operation? Okay. The simplest operation you will get for free, right, is a 2-fold operation about all these axes, right. Just give me 1 second. Okay. Yeah. So, the simplest operation one gets for free is a 2-fold operation about either A axis or B axis or C axis. It is one and the same. Okay. So, then the most simplest point group in a cubic system then becomes 2 3, right. So, in 2 3 I do not have a 4-fold axis of symmetry, there is no 4-fold axis of symmetry. by the way, this thing, right. So, simplest operation one gets for free is a twofold, either about A or B or C. This can be proved. Again, you take multiplication of various matrices, various 1 1 1, you have a threefold axis of symmetry about 1 1 1, right. So, I have written the matrix for this in one of my earlier classes. You can refer to class notes, or you can go back and then look at Glaser and Burns and then look at what these matrices are, multiply them and then try to prove to yourself that the twofold axis comes for free. Okay. So, there is no fourfold axis. So, again I keep repeating, in a cubic system it is not necessary that you have a fourfold axis of symmetry. At twofold is the minimum required, right. So, if I have 4 threefold axis of symmetry, what I get for free is a twofold axis of symmetry, not a fourfold axis of symmetry, right. So, the simplest point group that I will have is a 2 3, right. So, where 2 is the twofold axis of symmetry about all the 0 0 1, about A axis, B axis and C axis, and 3 is the threefold axis of symmetry about all the 1 1 1s. Okay. So, let us look at the stereogram of that. So, if I am going to look at a cubic system, see, this is the 2 3, right. Now, 2 3 has, you see, 3 twofold axis of symmetry and 4 threefold axis of symmetry, right. So, 3 twofold axis and 4 threefold axis. Okay. And you can see that the triangles represent the threefold axis of symmetry, that is about 1 1 1. These ellipses represent a twofold axis of symmetry, that is about the 0 0 1s and 1 0 0s, sorry, 0 0 1 1 0 0 and 1 0 1 0. Okay. So, I can have similar in a cube, hence I can have 2 3 m 3 bar. If I have 3 bar for instead of 3, if I have 4 3 bar axis, that is also fine, right. So, that also gives me a cube. Then instead of generating a twofold axis of symmetry, I generate an m, right. So, if I have 4 3 bar axis of symmetry, I get a mirror, but mirror about the mirror perpendicular to A axis, B axis and C axis, those come for free, right. I can have 4 threefold axis of symmetry and 1 fourfold axis of symmetry, right. Now, that gives me a twofold axis of symmetry, but this is going to be a diagonal twofold axis of symmetry, right. So, for example, 4 3 2, right. So, I have 4 threefold axis of symmetry here, right, and I have 1 fourfold axis of symmetry, right. Okay. Now, if I have 1 fourfold axis of symmetry, the other 2, right. So, this is the this is this is the 0 0 1. If I have 0 0 1, which is also a fourfold axis of symmetry, here I am imposing that 0 0 1 is a fourfold axis of symmetry. Just by having 4 threefold axis of symmetry, it is not necessary to have a fourfold axis of symmetry. But if I put the additional constraint that I have 4 threefold axis of symmetry, but one of the other axis, one of the the C axis is a fourfold axis of symmetry, then the other two axes also, the 0 1 0 and the 0 0 1, right, sorry, and the 1 0 0, they both become fourfold axis of symmetry, right. That is the regular, that is the normal cubes that you see, where there are 3 fourfold axis of symmetry, right. But that is, if I have 1 fourfold axis of symmetry in a cubic system, I should have 3 fourfold axis of symmetry, right. But it is not necessary to have even single threefold axis of symmetry. For example, m 3 bar and 2 3, right, m 3 bar and 2 3 have no fourfold axis of symmetry, right, whereas 4 3 2 has 3 fourfold axis of symmetry, 4 threefold axis of symmetry, sorry, 3 fourfold axis, and what comes for free are all these diagonal twofold axis of symmetry, right. So, this and this, right. So, and for twofold axis of symmetry, about so if I have a about 0 all these directions, about 0 1 1 set of directions, right, not just 4. So this is 1 2 3 4, but I also have 1 2 3 4 here. So I have 8 two-fold axis of symmetry, right, about 0 1 1, all 0 1 1 directions become two-fold axis of symmetry. Okay. So that's, these are the symmetry elements that are generated by having a 4 3 2 sort of symmetry, sort of point group. Okay. So with that we will stop here and continue from the cubic point group in the next class. So I'll see you again in the next class. Thank you.